There are several techniques we can use in the preparation of ethers. One is in the industrial synthesis of diethyl ether. You may have seen this in Organic 1. Essentially, it's the dehydration of two alcohols to yield the ether. And it's believed to proceed via an SN2 mechanism because we are dealing with primary substrates. You should be able to draw a three-step SN2 mechanism that shows the production of this diethyl ether here. Some problems with this are that it only creates symmetrical ethers. And to an organic chemist, those are useful, but they're not as exciting as unsymmetrical ethers. So we might be more interested in creating an unsymmetrical ether. So a British chemist by the name of Williamson invented the Williamson ether synthesis, or actually he invented an ether synthesis and later scientists decided to name it after him. So the premise is such that we take an alcohol that has one of our desired R groups on it, because this could be abbreviated here ROR, right? And of course an unsymmetrical ether might be ROR prime, which we cannot make using this industrial prep here. So let's say we want ROR prime. We would choose the appropriate alcohol, and we add NaH, sodium hydride, which is a strong base. It will produce H2 upon reaction with alcohols and leave us with the RO-, which is a good nucleophile. And the second step then could be the R prime connected to a good leaving group, and so we can do essentially an SN2 type mechanism for the second step and end up with ROR prime. So let's look a little more closely at how this might work. So let's say I want to make this ether here, isopropyl propyl ether. And so what I'm going to do is I'm going to react, and I'm going to show the OH bond so we can have a better idea of how the mechanism proceeds. But you should be able to draw this proton transfer mechanism pretty easily. So that's a proton transfer, and that gives us isopropoxide plus H2 gas. So you need to be careful doing this reaction. If you're not careful and let it get too warm or let it go too fast, you might ignite the hydrogen gas that's produced here. The second step would then be to choose the other side of the ether. So this would be propyl, so I want propyl chloride or bromide, and I can do the SN2 reaction here, and I end up with isopropyl propyl ether. And so you can choose, as long as this second ether here is primary, maybe secondary, but probably primary is preferred, of course, because we know that the SN2 mechanism requires sterically unhindered substrates. So most of the time we want to choose as our electrophile in this reaction a primary alkyl halide. So that means we could use ethyl chloride, or certainly methyl chloride would work well. I showed you propyl chloride, there's no reason that won't work. Isopropyl chloride, that works okay. But T-butyl chloride, no, we're not going to get any reaction with that, nor would we get a reaction with chlorobenzene, right? We cannot perform an SN2 style attack on that sp2 hybridized carbon. So if one of your R groups is aromatic, you may want to make sure that you start with that portion as your nucleophile and react that nucleophile with a more suitable electrophile. So let's look at one more option before we practice a little bit of these reactions. One other additional method is alkoxymercuration. I believe there's an E here. Demercuration. And you saw a hint of this in the addition to alkenes chapter in Organic 2. If we look at this alkene, we react it with HgOAc. first step. Second step is NaBH4. We know, and of course water as our nucleophile, we know that we're going to end up with the OH on the more substituted carbon. We could do the same thing with nearly the same set of reagents, except instead of water, we might substitute ROH. And then, of course, instead of the alcohol, we would put an OR group on our alkene. So now we might have a way to make the secondary, an ether with a secondary carbon on one side of it, if we couldn't do it via the Williamson ether synthesis. So this is the Markovnikov addition of alcohol across an alkene. We saw a hint of this in the addition alkene chapter. Now we're going to use it as a means of creating ethers. Alright, so let's look at these two ethers and see if there's a way we could create them. Here we have a secondary carbon, here's a primary carbon. So perhaps if we made this bond in our Williamson ether synthesis, that would be a good choice. And so if we had, let's see here. First I'd want to take this alcohol and remove the hydrogen. So that's the deprotonation reaction. And then I'm going to move my arrow this way because I messed up and left some crap behind there. If we take the primary alkyl halide, in this case a chloride, that should add the 3-carbon group we want and get us to that ether. In order to make this ether, we know that we cannot perform an SN2 reaction that creates that bond. We cannot do an SN2 reaction on an sp2 hybridized carbon, so we must make this bond. And so again, we would start with our alcohol coming from the aromatic group. NaH gives us the phenoxide, and if we let that react with methyl chloride, we get a nice snappy SN2 reaction and we could create that bond. There's actually another way to make that molecule, and it's not via the Williamson ether synthesis. Can you think of a way to make this molecule using another route? How about via alkoxymercuration? We see that the OR group, if we treat this as OR, the OR group is added to the second carbon of the chain. So if we had an alkene that looked like that, and we wanted to add ROH across that alkene and end up with OR, we could probably make that first ether. And so we know that we would need some mercury diacetate. And the second step would be NaBH4. I'm going to extend this arrow so it looks a little more clear. And if we choose ROH to be 3 carbons, we would make this molecule O with 3 carbons attached to it, which I hope you agree is the first molecule that we tried to make on this page. So we can make ethers a couple of different ways depending on what we want to use. Perhaps we had a whole bunch of propylene present in the laboratory. We didn't have any isopropanol for some reason, and so we decided to go at it this way. Alternatively, your supervisor may say, I don't really want you working with mercury because it is a toxic substance to humans, so let's try the Williamson ether synthesis, and then you would go up and try this option instead. So there are pros and cons to both options. Sometimes one might work better for various reasons, and it's these things we need to take into account when we are considering synthesis of small molecules.